to introduce the talk of Dmitry Kleinbock from Brandeis University with hyperbolic dynamics and intrinsic Diophantine approximation.
Okay, so thank you for coming, thanks to Misha and other people who became interested in dynamics and how it is related to other subjects. So this is some kind of a survey talk explaining how dynamics can be related to something which was not mentioned here in this conference, and this relation is a long story. So I'll try to basically survey various features of this relationship, and then I'll talk about something new that we can do using this relationship, explaining what kind of dynamics is involved and what are the consequences. So for me, actually, this part is the most important. I'll talk about both of these blue lines, but the most important part is this yellow. This red end, and my goal is kind of in an elementary way explain how one can go from one to another. So the new results are joint work with 3 people here. Some of it is published, some of it is still in preprint form. I guess mostly I'll talk about this line, maybe a little bit in the end about this one too. This involves, so I'll talk about this, so I have to explain what it means to have intrinsic Diophantine approximation. This is strange, bunch of strange words, so I need to set up some kind of language. So for the first 5 minutes, let me talk about the language, and I'll call it Diophantine triple. So there are 3 pieces of information. Start with M, which is some kind of a manifold. Maybe it's Rn, maybe it's something more complicated. And I have a metric there. Then you have a subset Q. So the story is basically you have some X here, and this is M. And then this script Q is a bunch of countable set of points, whose closure contains M. Finally, you have H, which is some kind of a height, right? So I have to use this one to.
No, I think I'm the worst situated.
But this is the boundary.
No. But for the L,
okay.
For you,
No, it's fine.
so
Okay.
yeah.
So you can approximate these points of M by this countable set, and the question is how you can do it, in what sense, and how to make this density quantitative. Okay? And well, let me go through a bunch of examples. So the classical example is how I approximate real numbers by rational numbers, real vectors by rational vectors, where X and also M is just Euclidean space. Q is a set of rational points, and the height is just a denominator of the rational number. Or sometimes you can imagine that this is RT, and you take a subset and you approximate points on this subset, say some manifold by rational points. There is also very rich science. Or something that I'll talk about today. I erase all these rational points and only look at points which happen to be in the manifold, and also start developing some kind of number theory. So of course this only works if we have a dense set of rational points inside. Okay. So just for a brief overview, let me show some other examples. This is actually, these Diophantine triples show up both in number theory and in dynamics, because you can start, you can let M be a phase space of a dynamical system. You start with x0 and you look at the orbits. The orbit is 0, and then if you know that the orbit is dense, you can ask a question of how dense is this orbit. For example, in an ergodic dynamical system, almost all orbits are dense, and then you can ask the next question. Well, you take random point y or some prescribed point y, and you approximate and ask what happens with this rate of approximation. So this example is about rotation of circle, in fact n or d n rotations of the circle. So have Zn acting on the circle, and the height is just the word length of the element of Zn. And you look at how you can approximate 0 by this, or how to approximate something else. This actually, there are many recent results on more general setup, where you just look at the dense subgroup of a Lie group, and then you ask how dense is the subgroup. Take a typical element, in which balls of small radius you can find elements of the discrete subgroup with a ball of radius r. And there are many tricky questions, some of them related to the spectral properties of the subgroup. Okay, or you can look at some discrete groups acting on some homogeneous spaces or other spaces and ask similar questions. So this is just, we don't need this slide anymore. And I want to also this is part of the language. Now I pick a function psi, and I say that the point x here, or actually it has to be here, is psi approximable if you can find a sequence of rational points Rk, which converge to x, and the distance between Rk and x is bounded by this function applied to the height of Rk. So this is a very general setup of classical Diophantine approximation. And let me say that psi is a Dirichlet function. If every point is psi approximable if you sacrifice a constant. So if you multiply by this constant c, then you can get everything.
So in this, is k equal to n or?
K is a yes.
Distance from Rk to x.
K is equal to n. That's the convention.
What is the Dirichlet function? Is there a basic example of it?
Of what?
Dirichlet function. Why is it called Dirichlet function?
Oh, I'll tell you. Okay, sure. Yes, it's because of the pigeonhole principle. Because that's basically one way to show that something happens like this is to subdivide into boxes and look for two pigeons in one box. Okay, so again, this is the point x, and you have Rk, and this distance should be bounded by psi applied to the h of this Rk. So this is now this. So another way of saying is that every x is c times psi approximable. For some c may be dependent on x. If this c can be chosen uniformly, let's say that this is uniform in Dirichlet. Okay. Now if you find the Dirichlet function, maybe you can make it even better. So why can't you improve it? Well, let's say that it's optimal if you cannot find a better function, which also works, and the ratio goes to 0. Okay, and now another way of saying it is that you can define points which are badly approximable with respect to psi. Okay, so points which are not in this, which are not in. Probably this is a misprint. That has to be union. Okay, so they are not psi approximable. So again, we can just look here. X is badly approximable with respect to psi. If for some epsilon, you always have this inequality like this, and the optimality of psi is equivalent to existence of a badly approximable point. So this is what number theorists do. They approximate, say,
Intersection or union?
Union.
yeah, this
Union.
has to be union.
Uh-huh.
Another dimension. Wonder how many other discretes you can find. All right. So this is what Kolem-Shvetsky does for Lilin, for example. He approximates some objects by some easy objects, and then he asks the question: is it optimal? Can it be better or not? So what are possible problems? You can look for if you're given such objects, such a given Diophantine triple, you can find an optimal function. If possible, make it uniform. If it's uniform, if it's optimal, you can look at badly approximable objects and see how many you can find. Also another general problem, which in the classical situation goes back to Hinchen, is fix this function psi and see how big is this set of psi approximable point. Does it have full measure? Does it have, if it has zero measure, what's Hausdorff dimension, and so on. So let me make this is.
I thought if you have a Dirichlet function, then there are no bad approximation points.
Yes, yes, but then right, but then
But then you say find the Dirichlet function, then for such phi.
Okay, it's a question of the constant.
Huh?
It's a question of the constant.
No.
That approximation means that the constant cannot be arbitrary.
yes, so psi is Dirichlet. This means that badly approximable points with respect to some c times psi is n. Okay, and then
I think you take intersection for all C.
yeah,
then you take.
yes, and then you take
Approximated by some constant.
but
you can
optimal optimal implies that badly approximable of some little c. So there exists some big c such that this is empty. And very often, for some c, this is not
So
empty.
badly approximable is, but you define badly approximable as the complement in M of the union of A of C phi. So I thought your constant varies. I mean, can you go to the preceding slide?
I think it has to be the intersection.
Has to be
It has to be the intersection. Okay.
No, that
You
is
might
correct.
have a complement.
So
Okay,
is it an intersection after all, or?
So,
I think it is actually.
yeah.
So the union is the whole
This
thing.
time, yeah, I guess this time I'm correct. I'm correct. So you right. So if some reason I got scared, but this is the correct expression. So that's what I mean. So at least in classical number theory, that's what happens. You find a function such that for some value of c you have something empty, but then at some point you decrease the c and you see something. And whenever it happens, you call this guy badly approximate. So maybe I should go to an example. This is just generalities. So what I always going to take is my Q will be the subset of rational points. H will be the standard height, which I'll just ignore, and I'll talk about the functions which are powers, and then I define this by psi sub c, and the norm will always be the supremum norm. And let me just briefly go through classical Diophantine approximation. This is an explanation why these guys are called Dirichlet functions, or this is why we decided to call them this way. So this is a theorem proved by Dirichlet. You can find solutions to this inequality when little q is less than n. Okay, and this of course means that you can put 1 over q squared, and this means that there's a nice function psi 2 of k equal to 1 over k squared, which is uniformly Dirichlet. Okay, and again, to remind you about the definition, that's what it means. You have infinitely many rational numbers solving these inequalities. Okay, and now it's optimal because there exist Bedler proximal numbers, which can be constructed using continued fractions. And these guys have full Hausdorff dimension, which was known since 1920s. And also there is theorem of Khinchin, which tells you exactly where this set has full measure, when the set has full measure, and when the set has zero measure. It's some convergence versus divergence of certain series. Here, this psi will be monotonic, which will always be my convention. Particularly one implication is that Bedler proximal guys have measure zero. Okay, so I wrote it. Actually, I wrote RD here, but the same thing. So maybe I should have talked about R. In RD, it is more or less the same, except for there are no continued fractions, but the proofs for some classical proofs for real numbers can be modified easily. What I want to do now is to switch to dynamics. Now this, what I wrote here in the previous slide, doesn't really require any applications of dynamical systems, because people knew this since a long time ago. But let me still spend 5 minutes to explain how, what does it have to do with hyperbolic dynamics and why hyperbolic dynamics is useful. And this is this end part. I think it's just interesting for its own sake, even though the results that one gets are not new. So what happens is that there is a certain homogeneous space that is responsible for these nice features of the problem, and the space is the space of unimodal lattices in R2. When you approximate vectors, you go up from R2 to R2 plus 1, and you start with a real number, and everything you need to know about a real number can be understood using a certain trajectory for certain lattice. When you act on it by a certain group element here. So let me draw 2 pictures explaining this and how why is it natural.
There's some colored chalk.
This is colored chalk. Okay, which is where? Okay, that's good. Maybe I'll use it somehow. So what is how do you approximate real numbers by rational numbers? It's very easy. You pick a real number alpha, you draw a line with slope alpha, and then you look for nearest integer points. And when you find the point here, it means that your alpha is very close to a rational number. Okay, that's nice, and the same works in higher dimension. Okay, and now you do this line is complicated. You make it simpler by shifting it so that it becomes vertical. And that's exactly what happens when you apply this transformation. So when you apply this transformation to the line, you have to move the integers also. So let me do it. So now this line became like this, and you have something strange here. And this is exactly lambda sub x. This is a collection of points on this new lattice. 1 minus x, 0, 1, z2. And now this is your approximation. Okay, if you have a integer vector pretty close to this line, it means that you approximate it well. So this is still too complicated. So next thing you want to do to this point is to move it closer to the origin by applying this GT, which contracts the second coordinate and expands the first coordinate. Now then it moves nicely, and if it was very, very close to the vertical line, it means that it will not be very far from the origin, of course. Okay? And so we have some epsilon, and that's this principle basically explains everything that I'm going to talk about. And again, in RD, your space is the SL d plus 1 R modulus d plus 1 Z, and the same, we can just think of this as RD and this is R, and the same thing will work. Okay. So now this is one picture. There is another picture which works when D is equal to 1, and it just identifies this space X, which is SL2R modular SL2D, with the unit tangent bundle to the modular surface. Then, if you have alpha here, the way you approximate alpha by rational numbers is related to the way the geodesic ending in alpha behaves. Doesn't have so when you look at this geodesic, and now you are on a quotient space, so you need to somehow make this Billiard trajectory, which you get by reflecting this geodesic along the edges that are identified.
Sorry, could you repeat? You want to approximate alpha? Or?
Yes, alpha. This alpha is the same alpha. Actually, probably I was calling it X. So maybe you should call it X.
And you look at the geodesic.
So if you want to do this, let me try to do this. It means that you need to apply. So this is a horizontal flow. So you need to apply the horizontal flow. A horizontal is actually like this. So if you don't want me to cheat, I have to do the following. I move here. This distance is exactly X. So my point is here. And this is so this is the initial. So this corresponds to Z2, and this corresponds to lambda sub x. And now I take a geodesic which starts at lambda sub x. But there is a fractional linear identification of this cycle with a boundary, so you might as well take x of the boundary. That's very often what happens. And now this good approximation corresponds to this geodesic going very high in the cusp. Okay. Any questions?
You mean, of course, hyperbolic distance?
Yes. So it's all hyperbolic distance. So let me kind of relate these two pictures by defining a nice function on the space of which I called L, not X. So this if L is the space of lattices in R2, delta is defined to be the smallest length of a non-zero vector, and this basically the logarithm of 1 over delta is basically the height here. And there are two important facts here. Minkowski's lemma says that you can always find the lattice point inside a ball of radius 1, and this can be used to prove Dirichlet's theorem. And Euler's criterion describes the compact subsets of this space. The subset is bounded if this delta is uniformly bounded from below, so there are no small vectors. So this is basically the picture that you should think about. It's the same picture as this one, and small vectors are here. So lattices which have small vectors are very high, very far away. Okay.
So this delta is like sort of a distance from a cusp.
Distance is e to minus distance. E to minus distance from a base point. Maybe with some power. Sure. Okay. So for example, this is one implication of this principle. A point is badly approximable, even in, well, I put here in dimension d, but it's not, we can think of, so Artem already knew this when d was equal to 1. If and only if the orbit is bound. So if you have a geodesic which will never cross this line, this corresponds to a badly approximable number. So what does it tell us? Suppose we know how to find a bounded orbit. This sounds much more complicated than finding the approximate number, but nevertheless, suppose somehow I constructed an orbit which is bounded by some other means. Then I deduce the fact that the Dirichlet function is optimal. Okay? And kind of a more sophisticated, more general version of this principle we wrote in a paper with Margulis in 1999 called Logarithm flows for flows of homogeneous spaces. And Dennis Sullivan before did it in 82 for basically a hyperbolic dynamic situation, logarithm for flows on hyperbolic manifolds. And it is more adapted to my to the question of related to Khinchin's theory. So if you have x and the sequence R1, R2, R3, and so on approximating x. Okay, so this good approximation corresponds to the following dynamical phenomenon. You have gt lambda x, and this orbit goes away, and then maybe it comes back, and then it goes away, and then maybe it comes back. And here you have delta less than epsilon, which depends on t. So in dynamical systems, this corresponds to something which they call shrinking targets. You have a family of shrinking sets, and the question is whether you can visit them infinitely many times. So it's a question of certain lim subset being of full measure. Then you have this family of shrinking targets, and you take pre-images, and you want these pre-images to behave well. And there is a very powerful theory here, which essentially comes from probability theory, from L2 estimates, which says the following, that if these sets mix up in a good way, then you can prove a theorem which says that if the sum of measures diverges, then almost all orbits belong to infinitely many of those sets. This is so-called dynamical Borel-Cantelli dynamics. Of course, I don't want to give details here, but there is a certain technology which, using this correspondence, allows to prove Khinchin's theorem, except for it's nobody needs it, because Khinchin did it in 1924. But still, it was a nice discovery that it's related to dynamics, and technically, if nobody knew about Khinchin, we could do it just as well.
This dynamical Borel-Cantelli is very general, like quantum recurrence, or not so general, like something more specific.
There are many quite general results. We don't have to live in a homogeneous space. There are, for example, results about moduli spaces, geodesics, and so on.
I mean, it's not like classical Borel-Cantelli or like Poincare recurrence, which are extremely general. It's not like that, right?
It's somewhat like this. So what do you mean by classical Borel-Cantelli?
I mean, if you just don't have any dynamics, if you have sequence of subsets of probability spaces, the measure diverges, then there is a
Then you don't know anything. If the series diverges, you need to have additional conditions. If the sum of measures converges, then you are happy
I
with
mean,
our
I'm talking not about dynamical parallel cantelli, and also there is purely dynamical, the Poincare recurrence, right? You don't need to know anything.
Yeah, Poincare recurrences, you just need to preserve the measure.
Exactly, this is what I asked. You still need something.
For Barrel Cantelli, classical Barrel Cantelli, or classical Barrel's part of Barrel Cantelli says the following: if sets are independent, then it works.
Yeah, I mean, in dynamical setting, it's just a measurable thing, or not.
Not really. I mean, you have to have certain independence of something.
It's about it's some theorems about measurable dynamics.
It's
not smooth dynamics.
right. So it's important, and something I didn't mention, that of course there is an invariant measure of this on these things, which is preserved by.
Yeah, but you don't assume any smooth manifold as a measurable state.
Well, I don't have to. In general, I don't have to assume any smooth manifold, but something has to be checked. And this something is related to the fact that these sets have to mix up in a reasonable way. So the preimages of these guys should become quasi-independent.
But it's still measurable statement.
It's still a measurable statement, but some technicalities are needed to prove the conditions that show up here. Okay, so I'm now back to the topic of my talk, which is at least hopefully will explain that the introduction of dynamics makes some sense, although some people may think otherwise still. So what I want to do is I want to study this arithmetical problem. You take a submanifold of Rd, which happens to have a dense set of rational points. Now it's hopeless to prove such theorems for all m, so you need to know something. And in this talk I'll make it very simple and just talk about spheres. So spheres are very nice objects. There are plenty of rational points, especially circles. In circles you have Pythagorean triples, which correspond to rational points. And there is some number theory here, which is not very sophisticated. But for high-dimensional spheres, it's trickier. And our approach also works for arbitrary rational quadratic hypersurfaces, and this is the subject of later joint work. So let me show a theorem which I think, well, at least for a while I thought that it is new. Maybe Koля will tell me that it was proved in 1937. And exactly in this form, or somewhat in a similar form. So this is a result which somehow we extracted using basically a similar correspondence between dynamics. Although in this there is no dynamics; it's more like statics. So you can find. Let me draw. So this is a sphere of radius 1, and certainly there are many rational points here, and if x is an arbitrary point on the sphere, you can always find a point of the form p over q, where p is an integer and p over q is the sphere, such that q is not bigger than n, and x minus p over q is bounded by some constant c, divided by square root of qn. And as a corollary, we get that the function psi1, which is just 1 over k, is intrinsically uniformly Dirichlet for Sn. This is what it means. We can always solve x minus p over q is less than constant c over q. And our work doesn't allow us to estimate how c depends on m. There are several papers of Koля, so maybe you can answer many questions about how to do it better than we do. So if you find some effective results, at least for dimensions 2 and 3, I don't know if something.
Now for all dimensions.
Now for all dimensions using this. So okay, so there are some estimates. For us it was a mystery. We kind of.
Could you recall what is phi 1?
This is what it is. Very nice one. Okay, so that's so this is this is what we got, and again there are many other ways to do it. So dynamics is not so important.
And what means intrinsically?
Yes, intrinsically means that I'm talking about this particular Diophantine triple. So here I have an ambient space, and I'm not interested in this pure Q. This is not part of my universe. I'm only on the sphere. Okay, so it is so it's a uniformly Dirichlet function for S n comma Qn Qd intersection Sn n plus 1. Okay, and so at least before this there was some work of Granic and Niveau with somewhat weaker results, although now maybe I should remove this slide because even this can be beaten by other methods before that. So one more result that we can prove is that this function is actually optimal, and the set of Bechdel approximal points, which is similarly defined as full Hausdorff dimension even. Finally, there is Hinchin's theorem, which is quite interesting. It turns out that so this is the set of psi approximal points that we can define like this, and there is certain convergence versus divergence condition, which we can check and prove Hinchin's theorem for approximating typical points, rational points in the sphere. So this was something that we were able to extract from a correspondence similar to this one.
And you are yourself and
so this is a paper with myself and Keith Merrill. So later we did it for arbitrary quadratic surfaces, and this is Leor Fishman and David Simmons also joined us. So what basically the reason for my talk was not to teach people how to approximate points on the sphere by rational points, which is I mean, either you like it or you don't like it, but at least there is a nice correspondence between one part of mathematics and another part of mathematics, which I find very amusing and playing with it for a number of years. So let me just explain how it works, and we shouldn't really worry about actually proving the theorems using this correspondence. So what you have to do is you take this sphere and you put it somewhere here. So this is your sphere, and then you introduce one more dimension, and then this Q, big Q, is the quadratic form which lives in Rn plus 2, and something which I call L is a so-called light cone, and why do I need it? Because once I have a rational point P over Q and I multiply by Q, I find a point P comma Q on this light cone, and which is now an integer point. So the problem about rational points on the sphere corresponds to the problem of integer points on the cone. Here, so the key idea is that so I want to do something similar to this. I have little x here, and I have P over Q here, and they are close if and only if Qx is close to P over Q on the cone. And so what it boils down to is a new object, which is a set of all integer points on the cone. here I was talking about integer points on R2, and now I live on this cone. Take this integer point, and again I want a good approximation corresponds to small distance between an integer point and a line with somehow spherical slope x. Okay, so x is a point on my sphere. I draw a line here. It is similar to what I used to have here, and I want integer points close by. And this is in case I didn't have a board. This is what this picture is about. And now, again, I can try to use dynamics by taking this vector and bringing it close to the origin, and this is what geodesic flow in certain space does. And when you do this, this vector follows it for a while, then maybe it will grow, but at some point it will still be small. So the same principle that worked in R2 or RT+1 works here. Okay. So what I want to do is I want to fix GT, which this will be P minus and this will be P plus, and this GT will move it this axis this way and this axis this way, and then the same geometric picture will show up here. You take these guys, you rotate them so that this x line passing through x, which used to be this one, now corresponds to the guy which is contracted. So there is a rotation of the sphere that you have to apply. And then you apply the geodesic flow. And again, good approximates to x correspond to small vectors in the lattice GT R sub x lambda 0, or R sub x is the rotation which sends this, so this is exactly R sub x. Okay. So this is how the correspondence is set up so that we can apply dynamics to solve dependent problems on the sphere. And that's what happens after rotation. Now GT sends these vectors close to the vertex of the cone. And this reduces the problem of approximation by rational points on Sn to the dynamics on a new space. So what is this space? This is the orbit of lambda 0. So lambda 0 was Vn plus 2 intersection with L. And now you apply various elements of the isometry group of this quadratic form. And you get the space of all such lattices. So these are the space of lattices in the cone. And it is equal to, it's a homogeneous space G modulo gamma, where G is, did I say G? G is SON plus 1, 1. And gamma is a lattice containing integer points as a subgroup of finite index. And the same compactness principle works. Again, if you want to, in this space, if you want to go to infinity, you have to contract certain vector. So this approximation again corresponds to excursion to infinity. Okay, so this is something which is not hard to prove. You look at pick real number R and look at the space of the set of lattices with omega beginning R, where omega is again the length of the shortest vector, and this set is